I'm going to show you in this presentation how to manually essentially read off phi and psi angles using Pymol. This presentation will give you a bit of a tutorial in passing on using Pymol, and it should give you, I think, more insight into the geometrical characteristics of the polypeptide backbone and their relationship to Ramachandran angles. Of course, you can determine Ramachandran angles quantitatively using the script that is available in CourseWorks, and for the evaluations for the course, you should certainly use that script, if nothing else, to check your inference to the Ramachandran angles. But going through this exercise manually will be useful in a couple ways. All right, so let's go back to the definition of the Ramachandran angle. The phi angle is defined as the dihedral angle of the N to C alpha bond. This sort of reference position that I like for the phi and the psi angles has the NH parallel to the C alpha C bond, and the CO bond parallel to the NC alpha bond. With all of these things parallel, this conformation has phi and psi both equal to 180 degrees. So as the arrow shows, this is the conformation of a polypeptide up at this corner of the Ramachandran plot. It is, although not most favored in terms of Ramachandran energy, it is a geometry that would make an idealized beta sheet interaction because the NH and the CO are pointing in the same direction, so they are poised to interact with an NH and a CO in roughly the same, with roughly the same Ramachandran angles in another polypeptide chain. So because this is the beta strand interaction, beta sheet hydrogen bonding interaction, sort of an easy point of conceptual reference, I tend to refer back to this this configuration, this conformation of the polypeptide, these Ramachandran angles of 180, 180. Again, it's sort of the edge of the beta sheet region, edge energetically, but sort of an idealized conformation to make beta sheet type hydrogen bonding interactions. The Ramachandran, so this is a Ramachandran angle. Let's go to the NH first. So the NH now parallel to the C alpha C, that's a phi of 180. That means the psi of 180 has the NH trans to C alpha C, and that's what's written here. Phi is 0 for C alpha C, trans to NH. So now at the psi angle, this CO bond parallel to NC is psi 180, and so that means the CO would be trans to NC for psi equals 0. So psi equals 0 for CN trans to CO. Here they're cis, so that's 180. 0 would have these things trans. So now when we look at Ramachandran angles manually, and we want to, of course, get the direction of the angle correct, it is important to note that we are always going to be going from N to C. So when we look at the phi angle, which we'll do first, we're going to start with N, and we're going to look straight down the barrel of this bond. And what we're going to do is we're going to make it so that if the phi angle were 0, that the C alpha C bond would be directly pointing horizontally to the right. So by this definition, for that to be 0, we would want this bond, the C alpha C bond, trans to the NH bond. And so what we want to do then is arrange the NH bond pointing horizontally to the left. If we're looking down the barrel of this bond and NH is horizontally pointing to the left, in the trans position, the C alpha C would be pointing horizontally to the right, and then we can just read off the angle by looking at the rotation relative to that horizontal position, and we're talking about the right-hand rule. So a positive rotation would bring, in that configuration, from that orientation, it would bring the C alpha C bond sort of rotate it down. word compared to the horizontal position. That would be a positive rotation based on the right-handed rule going from N to C. So that all sounds a bit abstract, but now let's go ahead and look at this in PyMol. So I will get rid of the PowerPoint presentation for the moment, and we'll move over to PyMol. The first thing I will do in PyMol is bring up a molecule. I'm going to bring up the one that's shown later.
It's 7 o'clock.
In the presentation. If you're online in PyMol and you know the PDB ID code, you can just type fetch PDB ID. This one we're looking for is 2HYD. I'm doing that. It waited. It found it. Cool. This is something called an ABC transporter. It's related to a rather famous, just a homologue of a very famous protein in the history of molecular biology called the multi-drug resistance protein, or the P-glycoprotein. That is a transmembrane transporter that promiscuously squirts chemotherapeutic drugs. Weekly basic chemotherapeutic drugs are squirted out of cells by P-glycoprotein. It has quite a significant impact clinically. Many people die when their tumors become resistant to chemotherapeutic drugs. This is a remarkable phenomenon discovered over 50 years ago. Tumor cells that become resistant to one chemotherapeutic drug were observed to simultaneously become resistant to many other drugs they had never been exposed to. Turns out this is the action of a promiscuous drug efflux pump, again called the P-glycoprotein. This is a bacterial homologue of P-glycoprotein. I am going to first just alter the display here. I'm going to go to the preset. I'll go preset pretty to begin with. We'll get an idea what this protein looks like. So these are actually alpha helical transmembrane domains. This is a homodimer. So there are two sort of interdigitated alpha helical transmembrane domains down here in shades of yellow, orange, and blue and cyan. Up here are two nucleotide binding or ATP binding domains in shades of green and red. This is an ATPase. This is from a protein superfamily called the ABC transporter superfamily. It uses ATP basically to power the export of the chemotherapeutic drugs. All right, so I'm going to now bring up the sequence. I'm going to have us, well, before I do that, I'm going to change the display. I'm going to change it just the other display that's quite useful, which is the B-factor putty. In this display, the color, both the color and the thickness of the backbone worm, as it's called, encode the B-factor, which is something you measure when you do a crystal structure. It reflects the degree of disorder or movement or displacement of each amino acid. It's based on the C alpha, or the backbone B factor, which is one of the backbone B factors. And so this reflects the degree of displacement of the C alpha atom, either dynamically within a single crystal, a single protein molecule, or statically in different copies of the protein in the crystal lattice. So blue means cold, immobile, very well defined, narrow. Red means hot, moving around more, more variable in its position in the protein in the crystal lattice. Okay, so I'm now going to zoom in and let's get some phi and psi value. Let's get a phi value and a psi value. I'm going to start at residue 150. This is exactly what's actually shown in the later in the PowerPoint presentation. Let me zoom in. Actually, I'm going to show. I'm going to take a wider region. Actually, I'm going to show for the whole protein the lines. And we're going to use those to the C alpha analysis. Now I'm going to just zoom in on the selection. And it's actually sort of a little bit harder to see this when the backbone worm is on, so I'm going to get rid of that. I'm going to hide. I believe this is the, I think at this point it's considering this a cartoon. Obviously, when you first use cartoon, it brings up a different display. I believe this preset B-factor putty script redefines the cartoon to be this worm-like feature. I think if I hit this, this will turn out, and it does. All right, and so now I'm going to highlight residue 150. And I'm going to find the phi. And so what is the phi? Well, once again, we want to look down the NC alpha bond axis. Let's see if I zoom in on this, whether it gets too magnified. That's a little magnified, but I think that's actually going to work for us. So we have this NC alpha. We're now looking down the NC alpha bond. If the NH were if, the 0 of phi, I'm sorry, yes, of phi, we'll have the C alpha C, right? So we want to look at the angle of this C alpha C bond relative to the NH. Now, one problem here is it's a crystal structure. The H is not actually shown, but we can know, but because we know this is an sp2 hybridized atom, we know that the NH will be coplanar with the N atoms bond to the previous C atom, in the C, the carbonyl carbon in the previous residue. So what we want to do is we want to get NH, what we want is to organize, we want to get this now so that we want the NH actually to be pointing horizontally to the left. When the NH is pointing horizontally to the left, that would mean the trans position would be horizontally to the right. When NH is trans to to the C alpha C, that is the 0 of phi. And so if the NH is pointing horizontally to the left, 0 of phi would be C alpha C pointing horizontally to the right. Now, however, because we cannot see NH directly, what we want to do instead of putting that, because we can't see it, we want to put that NH that we cannot see horizontally to the left, because that's coplanar with the N C I minus 1 bond. We will put that horizontally to the right. And so when we do this, right, so we have the NC for this, here we go. This is now, right, we're now going to rotate around that, right, we're looking straight down the NC bond. We are going to now orient this so that the NCI minus 1 bond is horizontally to the right. That means the NH would be horizontally to the left. And now the 0 position of the C alpha C bond would be also horizontally to the right. A right-hand rotation looking down the polypeptide chain, looking from where we are forward towards the C terminus, that right-handed rotation would be downward. And so basically the upward rotation is a negative rotation. And so now looking at this, we can see that this is something on the order of negative 60 degrees, right? That is roughly a 60-degree angle. This is the negative direction. The phi here is negative 60 degrees. So let's go back for a moment to the PowerPoint. Okay, and let's look at what we did. So we're saying we have a phi of roughly negative 60 degrees. A phi for 0 would be C alpha C trans to NH, right? So the C alpha C would be trans to NH. Here it's cis, where we saw it before when we oriented the NH horizontally across the plane of the screen. The C alpha C was rotated upwards. The positive rotation is this way. The negative rotation would be that way. It's a negative 60-degree angle. All right, now let's go on to psi. The trans position for 0 degrees, we would have CO trans to CO is, well, C alpha N is trans to CO for phi equals 0. So now in this case, because we can directly see the C alpha N bond, we will align that horizontally across the screen. That would mean the 0 position of psi has the CO going directly horizontally to the, we will align the C alpha N horizontally to the left. That means that the 0 position of psi C O bond would be horizontally to the right. So let's go ahead and do that back in Pymol. So this is again our residue of interest. So now we're always going to look from N to C. So we want to look down the barrel of this, right? In this case, we actually can directly see the C alpha N bond. Here we go. We want that to be horizontally to the right. Okay. I'm sorry, we want that to be horizontally to the left. We want to look down the barrel of the N C alpha bond. I'm sorry, we want to look down the barrel of the C alpha C bond, rotate it so the NC alpha bond is horizontally to the left. There we go. So now we have the NC alpha roughly horizontally to the left. The 0 position of the CO bond would then be trans to that, or horizontally to the right. It is instead rotated about 60 degrees upwards. And that, of course, once again, in this orientation where we're looking with the N terminus towards us and the C terminus away from us, the positive rotation by the right-hand rule would be down. So that means the CO is actually rotated about negative 60 degrees around the C alpha C bond. And so this is a psi angle of negative 60 degrees. So what we've come to the conclusion is that we have a phi and a psi that are both about negative 60. And does that make sense? Well, of course, in the Ramachandran plot, let's go back to that for a moment, negative 60 is sort of in the core of the alpha helical region. It would make sense, therefore, if this were part of an alpha helix, is it? Let's zoom out a bit. Guess what? That is an alpha helix. Let's highlight the residue we just looked at again. It looks like an alpha helix. Maybe if we go back to the preset zoom, I'm sorry, the preset B-factor putty. Yes, that is in the middle of the alpha helix. And so all this sort of fits together, and hopefully this is a useful presentation for you to, again, know a little bit more about, become a little bit more comfortable with using Pymol, and to understand in a bit more detail the geometric characteristics of a polypeptide backbone and how those relate to the Ramachandran angle. So we can just sort of double check all of this by running the script that determines that actually calculates the exact Ramachandran angles, and we'll see if that agrees with our conclusion here. So I will do that quickly. I will first have to dig up the script. Give me 1 second. It's in my Dropbox folder. Here we go. I will now just drag that script into the Pymol window on the Mac. And then it tells me how to use the script. It says report phi psi A1 100, measure phi psi angles of res 1 to 100 of chain A. It turns out there is some bug, not in the script I would say, but rather in the Mac version of Pymol. And it will not actually take the proper end residue of a polypeptide. But this seems to work properly if you actually just give it a residue range of, well, so this is chain A that we're in, I believe. Yes, this has told us up here. The Pymol has told us that this is chain A. That's what the A there means in that string. So it's chain A, and if we ask it actually for the actual residue range, it will not work properly on the Mac. But if we give it a ridiculous residue range of 1 to 1,000, even though there's not a residue 1,000 in this PDB file, it has worked in the past. I hope it works again now when I do this. It seems to be thinking, good sign. Thinking, 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 thinking. Crashing, 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 crashing. I hope not. Yes, and so it is determined the Ramachandran angles. Remember, we were looking, right? We're looking at residue 150. Let's go up here and check that out. Do we get the right answer? Did we properly determine these Ramachandran angles visually, manually? Go back to residue 150. And what do we see? Yes, indeed, residue 150. Negative 62, we guessed it was about, actually negative 63. We guessed it was negative 60. So phi is, this is chain A, isoleucine, number 150, residue 150, negative 63 to 62.95. Phi, negative 62.94, psi, so it's basically negative 60, negative 60. We correctly estimated the backbone Ramachandran angles from that exercise.